Have you ever, like, woken up in a pitch black room and just had to find a light switch?
Oh, absolutely. Countless times.
Right, so you can't see anything, so you're just shuffling forward, purely chasing that reward of flipping the switch. But, after doing that a few nights, you don't just memorize the footwork, you actually build this 3D map of the room in your head.
Yeah, you know exactly where the dresser is, right?
Exactly, all from just trying to reach one single goal. And that cognitive trick-taking, a really narrow, goal-oriented task, and extracting a universal understanding of the environment from it, well, it turns out that's not just a human trait.
No, it's really not. I mean, there's this fascinating 2026 paper we are diving into today called Inverting the Bellman equation. And it proves that artificial intelligence agents do the exact same thing.
Right, so our mission for this deep dive is to look at how simple goal-seeking algorithms secretly build perfect mental maps of their environment. But before we jump into the math of how they actually pull that off, I want to give a quick shout out to our sponsor, Silk.
Always good to mention them.
Yeah, if you are, trying to uncover where AI agents can make the most impact for your business, or maybe you need help with AI training, automation, or software development, you can discover all your solutions over at embersilk.com. Okay, so getting into this paper, we usually treat model-free and model-based agents as, like, totally different beasts, right?
Totally. I mean, historically, the assumption has always been that model-free agents just map states to actions based on rewards.
Basically completely ignoring the underlying physics of their environment.
Exactly. They just learn what to do, not how the world works. But this paper, well, it completely upends that division.
Wait, really? How so?
Well, the researchers mathematically prove that if you train a model-free agent on a sufficiently rich set of goals, it inherently encodes a highly accurate map of the environment.
Like a world model.
Yeah, a world model right inside its basic Q values.
Okay, wait, I need to pause you there because my understanding is that the math shouldn't really let it do that.
Oh, I know. It sounds counterintuitive.
Right, because if it is just, memorizing the most rewarding steps to reach a target, what happens when you block a path? It shouldn't know the layout of the city to find a detour, right? Like, it just knows the driving direction.
And that right there is the big breakthrough. Because if the agent only has one goal, you are totally right. It just memorizes the path.
Okay, so how does it get the whole map?
So if you give the agent a diverse set of goals, like go to the grocery store, then the park, then the bank well, those overlapping reward pathways force the Q values to factor in the actual structure of the maze.
Oh, wow. So the agent's value function just implicitly becomes a map of the world's transition dynamics?
Exactly. And to prove this map actually exists inside the agent, the authors created this novel algorithm called p-learning.
Let's break down how p-learning actually works, because I think it's so clever. Normally, the Bellman equation uses the environment's map to calculate the value of the next step, right?
Right, that is the standard approach.
But p-learning flips the algebra. It basically looks at the values the AI has already assigned to various steps across all those different goals, and then it reverse engineers the map that those values, must have come from.
Precisely. They use the agent's own value function to extract its hidden world model. And I have to say, the experiments they ran to test this were just stunning.
Yeah, they used continuous control environments, didn't they?
They did. They used a robotic arm called Reacher and a physics simulation called MountainCar.
And the crazy part is they only train these agents on really simple position-based goals, just like move the arm to coordinate X or move the car to point Y.
Right, but when they applied p-learning to extract that internal world model, they found the agent had perfectly understood entirely different physical concepts.
Wait, like what?
Well, for example, it understood velocity.
Without ever being explicitly trained to calculate velocity, that is wild.
I know. The agent just naturally generalized its knowledge. To reliably reach those positions, the most efficient mathematical shortcut was to just secretly map out the entire physics engine of that universe.
For anyone building or utilizing AI, this is a massive shift. It means these highly performant agents aren't just memorizing blind pathways.
Not at all. They're naturally developing this deep, really flexible understanding of reality.
It really is just pure optimism for the future of problem solving. I mean, simple learning mechanisms organically giving rise to robust, interpretable understandings of the world.
It is incredibly inspiring. And because we can now use tools like p-learning to, audit the models these agents build, it paves the way for incredibly adaptable, transparent AI solutions to some of our greatest human challenges.
Which is exactly what we want to see. And it leaves me with a final thought for you, our listener. If simple, repetitive goal-seeking naturally creates a complex, brilliant world model in machines, Well, what hidden maps of reality are you building just by pursuing your everyday routines?
That is a great question to ponder.
The next time you are fumbling for the light switch in the dark, remember, you are not just finding the light, you are mapping your universe. If you enjoyed this intellectually curious deep dive, please subscribe to the show and leave us a 5-star review. It really helps get the word out. Thanks for tuning in.